Welcome to this introductory video about the Duvernay formation fluid system, in which we will explore how the phase envelopes vary across the basin. Uh, the, the phase envelopes were created with my phase envelope printer running the equation of state model developed by Whitson. Whitson developed a basin-wide equation of state, able to describe basically all the range of fluids in the basin, which go from gas to condensate to oil, like in most basins do, right? In this case, they go from gas in the southwest to oil in the northeast. Basically, if we look at the basin in the direction it basically dips, right? Thermal maturity, right? Going more mature towards the southwest, where we have the gases, and then more immature fluids or liquids here, right? So let's start by going through this envelope. We'll explore them from lighter to heavier, basically. So we'll go from this one, this, and this. So yes, the 61711 is a lean gas condensate, right? My dashed line here representing the reservoir temperature. And then we have dew points all the way, right? Yeah, no critical point in this range of interest, which we are going to see is from 250 to 750 Kelvin, and from 0 to 300 bars, okay? And just again, 0% vapor red, 100% liquid red, and 100% vapor green, dark green, right? 0% liquid, dark green, right? So the most we can condense out of this fluid system is around 40 to 50%, around 150 bars, okay? My next fluid, 63169, is a richer gas condensate again, higher Craig content term, as we can see, as compared with the previous fluid. And in this one, we can condense more, like 60 to 70% of liquids we get at this condition, right? Around 150 bar. And interestingly, dew point, no critical point, right? And then this again, one is unstable region here. Basically, the dew points shoot upwards, right? Asymptotically. My next fluid, this is what we could call a supercritical fluid, right? Yeah, but we are just to arrive at the critical point. My reservoir temperature is just right to the critical point. So very well defined critical point, bubble points to the right. Sorry, dew points to the right, bubble points to the left, and yes, guess what? Around 200 bars, again, we have a tail and a stable tail, right? Shooting upwards asymptotically. At this point, I cannot tell you exactly what is this tail made of, if we have vapor liquid equilibrium or liquid equilibrium or vapor liquid equilibrium, but we know for sure this model predicts an unstable fluid in this region. Okay, my next fluid, 70055. This is a volatile oil at reservoir conditions, right? So this is a bubble point system. We are to the left, far to the left of the critical point. We have as compared to a previous one, again, we have a higher Craig content term here, and bubble points going down, and yes, around 175, we also see this behavior, this unstable region shooting upwards almost asymptotically. And more interestingly, this fluid exhibits a secondary critical point here right after the tail starts forming, see how those isocores converge toward this point. So, and my fifth fluid, my last fluid is a heavier oil. That's a lower bubble point pressure as compared with the previous fluid. The condensate term is also higher as compared to all the four previous fluids, and in the same region of interest, 250 to 750 Kelvin and 0 to 300 bar, this fluid does not exceed that unstable tail, right? Maybe if we explore lower temperature, maybe, but at the moment I don't know. So the rest of the animations in this playlist is going to showcase. We are going to scan these envelopes from in the temperature axis and in the pressure axis with our K values, our partition coefficients, basically, which is basically how each component partition between vapor and liquid, right? At every temperature and pressure, basically, that will help us understand why those interesting behavior, right? Like in the previous four phase envelopes where we have this unstable tail in the left, right? And okay, with further ado, thanks for watching, and I invite you to check out the animations in the next videos of this playlist. Bye.